So thank you very much. So it's really my pleasure to be here in Cargese with you. I will, in my talk, I will discuss some quite different things because I will not speak of disorder, mainly on order, and I will explain how you can use optical nanostructures, order one or second ones, in order to tailor specific properties. So, in the first part of my talk, I will first remind you some basic laws on dielectrics and metals, and then I will explain you how you can use either dielectrics or plasmonic nanostructure in order to do optics. So, what we will discuss in the following on materials and interaction with light rely mainly on the dielectric constant. And the dielectric constant relies, you can calculate the dielectric constant, but I would say that one of the most simple models that exists for describing the dielectric constant is the electron elastically bond. So I made you a small reminder what it is. So you suppose in this model, where is the laser? I don't know. Here? No laser. Is there a laser? Yes, here. So you suppose here that you have an atom with a kernel and an electric cloud. You apply a field here like this, and because of this field, you have a moving, let's say this, of the electronic cloud. That means that the barycenter of the kernel positive and negative charge is not at the same place. So you create here a dipole. And then you can describe the movement of the electrons by this equation. So here you recognize the acceleration. Here is a friction term, which is responsible for the losses. Here you have the bond, the fact that the electron is bound to the kernel. And here you have the field that you put in order to excite the system. And you can define here what you have, because the barycenter are not here, you create a dipole. And you can define the polarization of the material as the product, the mean value, because n is the density of dipoles, of the dipoles. And this polarization is in the linear approximation linked to the field here, and you can define what is called the polarizability, and this polarizability is directly linked to this quantity, which is called the dielectric constant, epsilon r, which relates the d to the e. So we will discuss here this dielectric constant, and this dielectric constant here, which is called also relative permittivity, is directly linked to the index of the material. So by this relation, here you have the square root of epsilon, which is linked to the index and the extinction constant. So the index is linked to the propagation of the field inside the material, and the extinction coefficient is responsible of the losses during the propagation. So you can plot here the real part and the imaginary part of the dielectric constant, which is here. And you have here for the real part a dispersion that you find here in the index 1 as well. And you can see that at resonance, which corresponds to this omega 0 of the bound electron, you have here imaginary part which is big, which corresponds to the imaginary part of this extinction coefficient. So, in what I will discuss with you is what we have when we are in, let's say, normal condition of operations. That means that we will mainly discuss what is happening here, not what we have in at resonance, which is as well very interesting, but we have to make choice. So usually, we will be in the case for which the index is larger than 1, and for usual dielectrics, index remain quite small. That means between 1 and 2. You can have indexes which are larger, but most of the dielectrics remain below 2. For metals, it's quite different because the electrons in this model, sample model, dual model, the electrons here is not, you don't have these friction terms, and you can describe the system like this. And when you solve the equations, I will not solve them, you can plot here what is the dielectric constant for gold, for example. So here you have the imaginary part. Here you have the real part as a function of the wavelength. And here I plotted the index part and the k part. So you can see that for one part, one range of the thing, you see that epsilon r is negative. And you can see that the k, the extinction coefficient, can be quite large. So that means that in the range for which we are going to work, you may have many losses by propagation inside the metal. So in fact, for gold, you see this yellow color. This is linked to this. When you calculate the reflection coefficient of the system, you can see that when you are in this region, so that means in the yellow region, so that means from here to this, so that means this is a yellow color, the reflection is equal to 1. That's why you have this color. You can use this, the knowledge that you have on these dielectric constants in order to calculate what sort of wave you can excite within the metals. So the first kind of wave that you can excite is a surface placement polariton that we will call SPP. And this surface placement polariton is a coupling of the electromagnetic wave, I represent it here, and the collective oscillation of electrons. And you have this wave, which can propagate just at the interface. And this wave has the specificity of being localized. So that means that this is an evanescent wave. So that means that if you calculate the distance on which you have intensity here. So here, what you find is that this distance is typically, if you have a gold-hair interface, 100 nanometers. And here, if you do the same thing in gold, you find typically at 60 nanometers wavelengths, 30 nanometers. So you will have a local field. And you have propagation along that direction. Then the field is very intense here, and it is used in applications, but the losses are high. So the losses, of course, depend on the wavelengths you work with. In the visible, typically you have a few microns. If you go to infrared, you can increase the length of propagation to 2/10, even a few hundred micrometers, but you have to go very high in the here. When you calculate this wave, you can express this wave as the link the k vector to the frequency. So you have the dispersion of the wave, and the dispersion is expressed like this. So here epsilon d is the permittivity of this of the dielectric, and m of the metal. And you can see that here, when as epsilon n can be negative, you can have a resonance of the system. That's why you have the plasmons. The fact that you have such dispersion, which is again expressed here, of the plasmons, makes that it's not so easy to excite the plasmons. In fact, if you take an incident wave, propagating wave, that it is expressed like this, and you want to excite this wave, what you need to excite it efficiently is that the projection of this propagating waves, which is a k parallel here, has to be equal to this. And you see that it's not so easy because you can change this angle of incidence. For example, if you take 90 degrees, you are in the case for which k parallel is equal to k1, which is here. But when you increase, diminish the angle of incidence, you see that your line is going like this. And here you have the placement dispersion relation, and you see that you have no crossing here. So that means that if you just take a wave like this, propagating wave, and you illuminate the surface of the metal, you have no plasmons. So in order to excite plasmons, you have several ways. I will not get into the details. I will just discuss one. So in order, you can use this configuration. I think this is a Krechmann one. For this, you take two media. You have the metal here, and you take two media. One is high index, so here glass, 1.5, and lower index, water, 1.3. And you illuminate, and here you have a very thin layer of metals, and you illuminate from the bottom. And in that case, as you illuminate from the bottom, and as this is very thin here, you can excite here on this surface the plasmons. And when can you excite them? Just because you are not in the same medium here and here. That means that your K vectors that you have here is not the same one that you have here. So that means that your line, that you have, your line which used to be here, is in this part crossing the KSPP. So here, at that point, of course I exaggerate things, but you can excite the plasmon. So that's the way to excite the plasmon. And in that case, when you do this experiment, so I illuminate the surface and I look at the reflection here, and I measure the intensity that I have here, what I get is a curve like this. This is the absorbance. This is the absorption, that reflectance curve. So here you have an absorption. And this peak here corresponds to the quantity of energy that you have put into the plasmons. So that means that when you do this measurement here, this is the signature of the coupling to the plasmons. So I discuss with infinite surface. So now I want to discuss the case of the metallic nanostructure. So in that case, I take a small nanostructure, that means gold ball, for example, diameter 16 nanometers, and I excite with a wave, electromagnetic wave, which is vertical in this direction. And what I observe here is that on this direction, I have extra intensity here and here. This is a kind of antenna effect. In fact, when you look at what you have inside your ball here, because of the field which is vertical, you can see, and it is oscillating, you can see that when the field in this direction here, you have accumulation of minus charge here and plus charge here, and reverse here. So you have creating here a polarization of the system, an oscillating polarization, which can radiate. And the traduction of this is here an extra intensity. So you can see that in this plot, here, what you have really at the very local point is an enhancement of 50. Ici, here, what you can see is that the size here is 60 nanometers. And you can see that your enhancement of light that you have is over a distance which is typically 10 nanometers. So it's really local field. You can calculate the polarizability of the system. So the polarizability depends on many things, the size, of course, but as well the metal, of course, which is expressed here, but as well the shape of the metallic nanoparticle. This is the expression that you have for a spherical one, but you can use other things than spherical ones. Here represented what you can observe, or you have seen already those kind of images in other presentations. Here, this is a solution of colloidal gold nanoparticles. And what is measured here is the absorption. So it is illuminated, you look at them, you look what is remaining to your eyes, or to your detector, and you see these colors. And these colors are reminiscent of the size of the system, because of this relation. And you have here the absorption as a function of the size. In fact, this effect is known for a very long time, but not understood at that time. For example, if you go to the British Museum, you have this beautiful cup. Maybe you have already seen this image of the liquor glass cup. Here in this liquor cup, the same cup in both cases. And in that case, you put light in the front, and you look at the reflection, what comes back to your eyes. And here you put the light inside the cup, and you can see that you don't have the same color. In fact, the reason for this is when you have these small nanoparticles, they can scatter light or absorb light. And depending on the absorption cross-section, I don't have exactly the same expression, but depending on the size of the particle, they can be efficient in absorption, which is the case of the small nanoparticle, or efficient in scattering. And in fact, when you have light inside the cup, what comes to light is what is remaining, so you lose the absorption. So that means that you lose the absorption of the small nanoparticles, that means what is more in the blue. When you look here in front, the reflection, in fact, you are sensitive to what's coming back to your eyes, but you have scattering in the forward direction. So what you have is just a reflection of what's remaining. That's why you have the greenish color. In these colors, in this cup, when you analyze them, you can see that there are small metallic nanoparticles, mainly gold and silver. That's the reason for which you have this color. So this is really reminiscent of localized plasmons that you have here. In fact, it was well known because when you go to church, these magnifical windows are made as well by the same techniques, inclusion of metallic nanoparticles inside the windows. And depending on the size of these particles and the metals that they use, you could have different colors. So now it's well understood. After this introduction, now I will go to dielectric nanostructure, and I will explain what sort of dielectric nanostructure you will use. So first, we will discuss the case of the fibers, well known. Then we will discuss the photonic crystals, 1D, 2D, 3D, and we will say a few words about light-matter interaction in cavities. So fibers, they rely mainly on the fact that you have index, and you have a fiber, and you don't have the same index in the core and in the cladding. So the most simplest one, the one that you have studied when you are in school, is this one. It relies on the fact you have your step index fiber, and when you have an angle of incidence which is small enough, you have total internal reflection, and you get the light. But if your angle is too large here, you have losses. So that's why you have a numerical aperture of such things. You can go here, you can see that these fibers are quite big, because you have this geometric waves figure. And you can see here that typically they have a size which is a few hundred micrometers. So very big for the core. You can have a more modern version with a graded index, and instead of having clear angles here, because the index is changing gradually, here you have this curve like this, and then the size is a little bit of the core is a little bit smaller because you go in the under of 50, 100 micrometers. And the most important one is this one, which is a single mode fiber. This is the one that you use for telecommunication, for example, everywhere. And this view are not valid in that case, and you have to speak of propagation of modes. So in that case, single mode propagations. And in that case, that's a way to avoid to the maximum the dispersion, the losses, and they are optimized for telecommunication at 1 micron 5. They are much smaller. That means that the core here is about a few, I will say, about 1 order of magnitude larger than the wavelengths. So much smaller than this, but you see, this is 10 microns, typically. This is the one that you can use in integrated inversion, because one of the challenges when you do nanophotonics and nanostructure, optical nanostructure, is to put all this nanostructure on a chip in order to have something, a device which is more useful than a big device that you can use. So this is one version of what you can have on a chip. So on a chip, what you can use, for example, are waveguides. So exactly the same thing that I showed you before. Here you have a high index core, in that case it's silicon, and here you have hair. So you have a waveguide which propagates light. You may have on silicon, depending on the wavelength you use, losses. But on a chip, if your chip is 1 millimeter long or a few hundred micrometers long, you are not so sensitive to losses as when you use a fiber which is thousands of kilometers long. So the question of the losses when you are in integrating version is not such a thing. Then you have to couple, and this is really a challenge, fibers, which are represented here. So you have several core fibers here, to this width to this wire. And this is not so trivial because you see the widths are very small, 400 nanometers, so you have a lot of technology to do this. So in order to do this, in any case, what you need is very practical because you have a chip, but you need technology to do this. Clean rooms, very big clean rooms. Typically, you see the size of this is a few hundreds of nanometers, which is small, but not very small. So I suppose that you are more familiar with mirrors that you have on your experimental room. And when you use mirrors, you may say, okay, I take a metallic mirror, but when as you know, the metallic mirror is not so good because you have a reflectivity, which can be 95%. So if you have hundreds of mirrors on your experimental room, you can see that 5% of loss for each mirror, at the end, it makes a lot of losses. So what you prefer is this, is dielectric mirror, which was specially designed for a specific wavelength or range of wavelengths. And how do they work? So I will just tell you the optician point of view at the moment. So that means that let's consider that you have a substrate and you put a layer, which is quite thin. And you have, because you have here difference of index here and here and here and here, you have reflection at each interface. So if you design well the thickness, the optical thickness of your layer, you can be in the case for which you have constructive interference, and so that means that you have reflection of your system. On the opposite, if you choose another thickness of your coating, you see here that you can have destructive interference. In that case, you have transmission. So this is a general way to understand what is dielectric mirrors. When you buy a dielectric mirror, it's a little bit different. So it's like this. Instead of having one layer, you have many layers. So a few pairs of high and low refractive index, and each layer has an optical width, which is typically λ/4. When you do this, you are in the situation when you have constructive interferences and you have a mirror. So when you look at the reflection as a function of the frequency, you have something which is like this, and you can see that you have a reflective which is very close to 1 for a very large, for a large or not so large range. In fact, the fact that the range is large or not depends on this and the number of pairs that you have chosen. So this is the optician point of view. I will take another point of view, which is this, is the point of view of the solid physicist. Of course, you will say, okay, for describing a mirror, I don't need this, and this is true. But we will come to more complicated situations when you cannot just explain this with interferences. So let's consider at the beginning that I have an homogeneous medium here, and I want to propagate along this medium, let's say along X. When I do this, I can plot omega as a function of kx, and this is very trivial. You obtain lines. Then now, I want to describe the Bragg mirror here with these pairs of layers. And two layers has a periodicity, so I have a periodicity of lambda, which is expressed here. And what I want to get is this function, so the dispersion curve. So when I do this, I'm sorry for the animation, this came after, so forget these lines. When I do this, so I will say, okay, I have a propagation along X at the beginning, and I have a periodicity, and the Bloch theorem says that if I have a periodicity of the material, I have to find the same periodicity on the dispersion relation. So that means that what I get is I take these lines, which are here, okay, and I repeat them with the same periodicity. And the periodicity is here in terms of the reciprocal states. So that means I don't speak of lambda, I speak of k here. Okay, but here you have crossing, and light does not like crossing and degeneracy. So that's why there is an opening of the thing. In fact, when you do this, that means that here, for this range of wavelengths, you have no possibilities of finding a k vector. So in other terms, if I propagate along the k vector, I want to propagate along the k vector, and I want to enter the materials at that wavelength, at omega 0, there is no possibility. I cannot find a k vector. So that means that the propagation inside the material is forbidden for this k vector. So we can go one step further. So in that case, I take this material, I propagate either like this or like this. In Y, this is homogeneous, so I have the line, and here I have the gap. When you do this, I don't represent all the k's because we can prove that if you have symmetries and periodicity, you can restrict your, as it is periodic, you don't have to represent everything, and you can restrict to what is called the Brillouin zone. This is this. And this, you obtain the gap here, and this gap increases when you increase the index between the two materials. Here we are in the case for which the photonic band gap is not complete. That means that if I choose a wavelength which is here, there will be no propagation along X, but there can be a propagation along Y. So if I want to enter the material here, it cannot propagate along X with frequency which is here. So as it does not propagate inside the material, the only possibility for this wavelength, for this wave, is to be reflected. So this is the solid physicist point of view to explain interference Bragg mirrors with band gap point of view. Well, of course, it's a little bit too complicated, and interferences are completely sufficient to describe the Bragg mirror. But in case if you go to more complicated case, for example, this, and represent here two realization of photonic crystals. So here you have pillars or holes. It depends what you have. Here I represented the band gap, the band diagram for this realization. This can be realized in clean rooms. And the typical size of this, it depends on the wavelength you want to work. But as everything here can be physically understood in terms of interferences, you are always in the situation for which the periodicity is close to lambda, the wavelength for which you work. So you can calculate by the same way, don't go into the details, the band diagram. You have it here for this photonic crystal. So I will just say a few words on this. So here what we present here is K. So this is the K space, you are in the reciprocal space, and instead of presenting all the direction of the K, which is much more complicated, you restrict your representation to specific direction, which has a remarkable direction of symmetry of your crystals. For example, here, for this hexagonal case, in the reciprocal state, you have here this, representation here of the K, the main direction. So you have the P, the gamma is the center, so K equals 0, and you can go to the P, go to the P to the Q, and come back to the K. So in other words, when I represent here the band diagram, I always start from the center, so K equal to 0, and I go here to Q. So I represent what is the dispersion, omega as a function of Q, of K, when I go from this point to this point. So here you have this K vector, and here you start from 0. That's why it is a line, because you propagate over a line. And then you take your K vector, which is here, and you bring it to P. And you have this line. And here you start from gamma, and you go directly to P. So this is the band diagram. And you see that for many wavelengths, for example, this wavelength, you can find several values of Q, which permit the propagations of your system. Of course, you can see that here, whatever, for this gap, whatever the wavelength you choose inside the gap, you have no K representation. So the light cannot propagate inside this wavelength inside the photonic crystal. And you have reflection. I will come back to this after this. Another important thing when you have this is to say that, where is it? It's coming. That the velocity, the group velocity, is the derivative of omega as a function of k. And when you look at specific points, or maybe, yes, you have two specific points. The first specific point is this one. You can see that the band is flat. So that means that the group velocity is very low. And if you propagate at that frequency along that direction, which is something between Q and P, so that direction about, then the propagates very slowly, so you have a slow light. So it's very good for interaction. If you go here, for example, you can see that you have a high curvature and you have a change of velocity which is quite high if you start from this point to this point. And you can use it in order to do super prisms. So in normal crystal, you propagate, you send the light between 0.9 micrometers and 1 micrometers, and it goes straight away. In a photonic crystals, if you are exactly at that point, you can have a prism effect. So that means that you can engineer, depending on what you choose as the specificity of your photonic crystals, you can achieve specific properties that you could not achieve with a normal material. Here, you can use, for example, photonic crystals in order to do guiding. It's quite simple. You choose a wavelength which is within the photonic band gap, so it cannot propagate inside the photonic crystals. And you create a defect, so that means no photonic crystals here. When you send the frequency which is within the band gap, it will not be able to propagate here, but it can propagate here. So that means that you can create waveguide inside your photonic crystals with very high curvature in very small distance. So it can be very interesting. Here I put you an example of slow light. Here you have nanowire, I showed you before. Here you have a piece of photonic crystal. So here is normal velocity, and here you have slow light. So if you want to interact with the material, for example, to make nonlinear optics, is very efficient. So in order to resume these 2D photonic crystals, in fact, they are very interesting because you can engineer the geometry as you like, as long as you can fabricate it. They are integrable because they are 2D structures, so this is very good for making chips. The problem is they are quite difficult to fabricate, so if you don't have the big clean room with all the materials that you need, is very difficult to fabricate. And they are quite sensitive to defect, so you need really high quality photonic crystals in order to see this. Of course, what you see here, I made a description as a physicist, solid physicist, so this, but of course it's always interferences. You have not to forget this. The only thing is describing this with interferences is very difficult because the geometry is very difficult. That's why we use this solid physicist approach. But this is interferences. And you can see that if you have defects inside your photonic crystals, the interferences will not be as efficient. So the very specific properties that you want, band gap or prism or whatever you like, are not so good if you have defects. And you have losses, but as you tell you, as long as you don't have too much, you don't propagate over too long distance, is not a problem. In fact, propagating to a long distance, you can do it with fibers, but in fact you have this fiber, which are photonic fibers, but it's quite different with fiber because you do not do it in a clean room, well, in another clean room, but what you take is normal fibers that you iterate like this, so you can have very high quality fibers. So in fact, for photonic fibers, we can be hundreds of meters. What you can have is either plane defects, so you have the band gap, you have here the defect, so if you choose a wavelength which is within the band gap, it cannot propagate here, but it is propagating inside the defect. It is very well confined, very efficiently confined. So in fact, it means that it is very interesting because if, for example, if you propagate a very large distance with a very high confinement, you can reach huge energy on very large distance. That means, for example, for nonlinearity, is very good. So, in fact, you can buy it as well. If you take, for example, this wavelength in the photonic crystal fiber, which is designed for this, you propagate over hundreds of meters. And because of nonlinear effects, what you get here is a white spectrum. This is what is called a continuum, supercontinuum, or a white laser. This is commercially available. Here you have the hollow effect, same idea. Instead of having matter, you have vacuum. And the difference here is that if you design well, when you propagate here, you don't have dispersion because you don't have materials, you just have vacuum. So that means that you can guide over long distance without dispersion. So that means that if you design well your geometry here, you can propagate several wavelengths without dispersion, which is the limitations in telecoms. So we discussed 2D, 1D. So now I will discuss 3D. And 3D, as you can imagine, is much more difficult for us. But for nature, it's not so difficult. In fact, 3D, you find them. For example, here, this is an opal that you can find in the nature. So it's a very beautiful stone. When you turn it, you see the color changing. In fact, it's quite easy to do in the lab. If you want to do your own opal, you take silica balls, same size, typically in our case 300 nanometers of size. You have here a glass plate here, and because of self-organization on the meniscus here, what you get is a crystal, a CFC crystal. And you can have image here, large size, and here a more focused view. So you can see you have this piece of crystal. In fact, I represented here an opal. You can see this is the same device here, the same plate that I represent here. Here, the only thing we change is that I change the angle of illumination. So here is a normal incidence, and then we increase in the incidence. And what we see is we change the color. In fact, as a mathematician, I like interferences. In fact, you can describe it quite easily with this to say, okay, I have a CFC structure. And CFC structure means that you have plane for which the density of matter is higher. So in that case, I can interpret the color here, and it works quite well, modelize here, that by a reflection on the dense plane of matter. And when you do this, you obtain constructive interference for a given incidence for a given wavelength. And of course, when you change the incidence, the wavelength for which you have constructive interference change. And that's why you get this color. It's not as beautiful as this, but just because it's much more ordered as this. And this is the reason. And typically here, this is 1 centimeter square. Here, the size on the crystal here is 1 millimeter, something like this. This structure, they are well ordered, but you can see they are not perfectly ordered. You have a kind of transition between something which is a crystal, a real crystal, and something with a certain level of disorder. In fact, in nature, you find this transition between order and disorder. So, for example, I present here morpho wing. A morpho wing, when you look at the microscope, you see two things. Optical microscope, you see scales, which are represented here. And then you want to go to further to look more precisely. So you have to go to an electronic microscope. So when you take this scale here, you get here to this. So you see the scale here. Here you have which here, which are here, in fact. And then you can increase the view here and see here the structure which are complicated. In fact, the fact that you have the blue color here corresponds to the fact that you have wedges. So here you can see that you have lines of matters, and you can describe it either as a bandgram, a photonic band gap, or as interferences. We have lines, and you have here a weighting, a kind of weighting. But you see, and that makes the blue color. That's why when the morpho is flying, you see the color changing from violet to blue. In fact, here, you see it's not so regular. And that means that you have this color, but in fact, the fact that you add disorder in the system brings some robustness. That means that the properties is not so sharp, but it's much more robust and much more broad in spectral way. Here, the structures that you have here are very small, so I don't have the scale. See, I have the scale here. And you have no optics effect at this scale. So that means that when you look at this here, and you put a drop of water on the wing, what you see is something like this. So here you see in blue, this is the scale, and here you have the drop of water. And you can see that you have hyperhydrobicity, which is linked to this structure. So you see that nature makes the fact that because you are at different scales, it brings you several properties, optical properties, but always hydrophobicity. So I discussed quite in details what you have with the morpho, but of course, if you go to something, you have many insects and other animals in life which have other character. So we discussed the guiding. You make a line of defects, but you can discuss at the same way the storage. So for this, instead of making a line of defects, you make a region of defects. So here, for example, you inject by some way the light corresponding to the photonic band gap. It cannot propagate, so it's stored inside the defect. And this is expressed, for example, for here, you see the resonance of the mode at a good wavelength. You can do laser with this. This can be done as well with 1D, and here you have Bragg mirrors, so you can see typically a few micrometers of diameter and 10 in height. So this is just Bragg mirrors. In order to do the defect, a resonant defect, what you need here is to have a λ/2 defect in the middle. And you can have a resonance, which is either a Fabry-Perot, or if you put emitters inside, what you get is a laser. You can go further, you can buy it such object. Here I present an example of a company which has been funded by Pascal Sellard in the C2N on quantum computation. So here you have the pilar, so it's quite difficult to see it, but the pilar is here in the middle. And here you have a device in order to be able to electrically excite the single emitter that has been put just in the middle. Yeah. This is put on a chip, which is here. And then what you can see here, quantum emission of single photons, which are single identical, so we have all the good quantum properties. So I will switch now to plasmonic nanostructure, to another point of view. And for this, I will discuss what you can do with plasmons. So plasmons are very efficient for sensors. For example, here we discussed already what you can do with SPP. So we discussed the fact that if you want to excite the SPP, I didn't represent the SPP here, but it is at the surface here. You excite the SPP, you collect the reflection, and what you obtain is this curve here, and the peak here, the maximum of absorption that you have here, is linked to the fact that you put energy in the plasmons. In fact, when you change the index here, you change the crossing between the propagating light and the plasmons, and you change the wavelengths of excitation. So that means that when you change by the little factor the index here, you have a shift of the resonance. And this can be detected. So you can use it for making a biosensor. So in that case, what you do is you have this configuration. You put it on the surface, on the gold surface, so chemists can do this, or biologists, a functionalization, so that when you have your target, the target wants to fix on this surface. So if you want to detect the target, you then send water with molecules, these molecules or not, this target or not this target. When you have these molecules, these target molecules, they fix it and they change the index. And as they change the index, you have a shift in the resonance and you can detect it. So this is used for biosensor, commercially used for biosensor. And this is linked to two things. First, the fact that you have a shift of the resonance. Secondly, the fact that when you are you have a high confinement of the light at the surface. We discussed before what you have as a resonance where you have a gold nanoparticle. And we discussed the fact that you could have excitations of local field, antenna effect, with the gold nanoparticles. In fact, when you take two particles, here and here, very close, so typically 10 nanometers, you can see the excitations that you have, the increase of intensity that you have here and here, but you can see that between the two particles, because you have plasmons which is excited on both ways, you have a resonance, and you have extra intensity here. So this can be used for detection of molecules. So here you have here a dimmer antenna. You put here molecules, and when these molecules are inside this dimmer antenna, what you can see is fluorescence, which is very high. So here you can see that you have molecules everywhere, but the only place when you see fluorescence are places for which you have put your dimmer antenna. So in fact, when you do this, you can reach again to the detection in comparison to what can be do with a normal microscope on a glass slide by a factor of by 4 orders of magnitude, and you can detect very small volumes, a MacArray detector with very small volumes of molecules. So I hope I have convinced you that you can use plasmons and nanostructure in order to create sensors. Now I switch to another point of view, which the use of plasmons in order to excite specific properties of the light. So for example, here, we consider here this nanostructure, which are U ones that you can do in your clean room, very simple clean room. This is quite not so difficult to do. You can see that this typical size is a few hundred of nanometers. And the objective here is to see these U are not chiral. And the objective here is to see if you can use non-chiral materials in order to enhance the chirality of what you observe. So in that case, you have these materials here, and you can excite them. You can illuminate them with two waves, one which is horizontally polarized and one which is vertically. And you measure the absorbance. And you have peaks of absorbance which correspond to the modes that you excite, depending on the polarization. And in fact, I will focus mainly on this mode that I will discuss. So on this mode, what I represent here is this is the U, and here you have a simulation of the field that you have. So when it is wet, that means that the color means that the quality of the excitations, and the arrows here correspond to the direction of the field. So in fact, when you are here, what you can see is you have field like this, field like this, field like this. So first, what you can say is that you have here something which is like this, which corresponds to the magnetic dipole. Then, when you add these three arrows, you can see that you can suppress this with this. So what is remaining here is just this electric dipole. So here, when you are at this resonance, you have the superposition of a magnetic dipole and electric one. And this magnetic dipole and electric one, they are excited by an oscillating wave, and they can radiate. In fact, this is what you can get. So I resume here. You have your U. You have the magnetic dipole, which is due to this current here with the M, and you have the electric dipoles. When you have an electric dipoles and you are in homogeneous medium, you know that the emission diagram is something like this. This is P, and when I present it with arrows the direction of the field, and you can see that you have many directions of the field, at this case at u theta, but the important thing is that mainly it is oriented along the P direction. Then I take the magnetic dipole. I represented here the electric field which is created by this magnetic dipole. This is like this. And you can see that if P is like this and M is like this, you can have interferences between the field, which is mainly in the direction of the P, and the field of the M, as far from here and here. So you can discuss the interferences that you have. In fact, if you want to do it more mathematically, you can define here a polarizability, which is a little bit more complex than what I presented at the beginning, which prove you that you can create an electric field from P with a polarizability, electric polarizability, and you can create as well an electric field from the magnetic dipole with the magnetoelectric polarizability, which is here. So you can add both, and the important thing is to notice that when you scale this, here you have a I here, which corresponds to the dephasing of pi over 2 between the two fields. So that means that when you add the two fields, you have a dephasing. So that means I can switch to circular or elliptical polarization depending on the value of the modulus. So this is what we want to exploit. In that case, what we have here are resonators, which are not chiral because the geometry is not chiral, but depending on what you do, you can exploit by planning on the relative value of this and this, which has sigma plus or sigma minus. So this has been done in the experiment. So for example, you have here this resonator, you have an incident wave, and you have the normal incidence, and you can excite the resonator by turning along this normal incidence. So you have the phi here. And you excite it by non-polarized light, and you collect what you have. Because of this effect that I have explained you before, what you collect here are either, depending on the direction of excitation, are either sigma plus or sigma minus. So that means that mainly sigma plus or sigma minus. That means that when we calculate what we call the circular dichroism, I calculate the difference of intensity between the light which is polarized with sigma plus minus the light which is polarized with sigma minus. So this is the circular dichroism. You can prove that depending on the if you illuminate in this direction or this direction, the light is mainly sigma plus or mainly sigma minus, which is expressed here. So here is mainly, let's say, sigma plus. I don't never remember if it's sigma plus or sigma minus. And here is the reverse. This can be used, example, for coding information. So here you have an image. You make the pixelized view of the image, and for each pixel you want to describe the color as a function of the number of hues that you put. For example, if you are gray, you don't feel the whole palette of hue nanostructure. So as you are looking to, as for reflection, of course, if you don't have the whole palette here, you will have gray. So you do this. And then you want to have the information of the image. So for example, if you illuminate here with a linear polarization, you lose nearly completely the information of the linear polarization. Here you can see that we change here the hue with different direction of the hue. It's just because when you do the things, you can have remaining polarization, which is just artifacts. So it's just you have the same effect, but you have this. Then what we do here is the same experiment. So we excite with sigma plus or sigma minus. And when you calculate the dichroism, you can see that you can find again the information. This is a way to hide an information by linear polarization. So now I will try to explain you how you can use nanostructure. The work before has been done by Bruno Gallas in INSP. This work has been done by Mathieu Mivel, my colleague in ISP. And now I will try to explain you how you can use nanostructure in order to enhance the response of magnetic transition. So, for example, here you can consider erbium-doped nanoparticles, europium-doped nanoparticles. And when you look at these nanoparticles and the transition of these nanoparticles, in fact, you have two electric ones and one magnetic ones, and they are not at the same wavelength. So, here, what we consider here is a substrate on which we have put rows of metals, just wires of metals. So here you have the top view, and here you have the side view, and here you have aluminium, and then you have nothing, and so on. And because of this, what you can create, for example, if you are here, you see that you have your metal here. Here you have nothing here, and then again metal and so on. So what you do is you create a plasmonic cavity, because you can have oscillations inside this plasmonic cavity. And then the question that you want to address is, what is the distribution of field that I have within this plasmonic cavity? And of course, what we expect is, as we have propagation of wave, we expect stationary wave, just like a Fabry-Perot. So remember, what you describe with plasmons is always local. Look, if you want to see the field, which is at the surface, you have to look very close to the surface. That means that you cannot do it with a normal microscope. So you have to do it with a SNOM, scanning near field optical microscope. That means that you take a microscope which is made of a fiber, which can be metallized or not metallized, and you put it very close to the surface. That means very close, at less than 10 nanometers away from the surface. And you scan along the surface. And when you have a wave, you have diffraction of the wave because of the tip. You can collect this information and have an information of the field that you have at the surface. So this has been done here. So here you have the plasmonic cavity, and we scan along this direction. And on the tip here, you can see that we have put here a particle, so nanoparticles of this. So when we scan along the direction, when we have a resonance of the electric field, we will excite mainly these transitions, the electric one. When we have a resonance of the magnetic field, of course it is an electromagnetic field, so we have both, then we will excite this transition. So this has been done, and you can see that this corresponds to the response of the magnetic transition, because you can separate with filters, dichroic filters. So this is the response of the magnetic transition, and you have here the response of the electric one. And you can see that they are completely in opposition as expected. So this has been done for several lengths of cavity. You can go further and say, okay, now I don't want to scan only the field that it is on the plasmonic surface. What I want to do is to enhance the response of the magnetic transition. And for this, you can use an antenna. So we have always discussed of the dimmer antenna. So you have as well the bow tie antenna. So for the bow tie antenna, you have here two nanoparticles here, and you put them very close. You have here an edge, here and here, and you put them very close to each other. Few nanometers, a few 10 nanometers. 10 nanometers to the maximum. And when you apply a field, you have plus, you have minus, it's oscillating, and because of antenna effect, you have a huge field which is here. You can do the same thing with a diabolo, and you see it's quite different because here you have matter, you have always metal here, and when you do this, the difference is when you apply your field, you have the charges going from here to here, so you create a current. Here you have a reservoir of electrons, so you create a current, and because you have this current here, you create a magnetic field locally. So you can use these diabolo things in order to enhance the magnetic field that you have in the middle and use it to enhance magnetic transitions. So for example, here, this is a calculation of the diabolo. You can see the magnetic field in the center, and you see that there is nothing here for the electric field, but here, on the top here, because of the antenna effects, you have maximum of intensity, but you have nothing in the center. So now, this is calculation. This has been done experimentally as well, but I don't have time to present the experiment. So here you have the diabolo, and it has been calculated the response of the system, the response of the what is the magnetic field, or and what is the decay rate, and the radiative decay rate, so the intensity that you can get if you put a particle, a magnetic or electric particle, just close at 10 nanometers from the antenna. And the response is here. If you consider, for example, the radiative decay rate, it corresponds to the quantity of photons that you can expect to get. You can see that for the electric field, you are here, and for the magnetic field, you are here. So you have a clear enhancement of the response of the magnetic components, which correspond to the fact that here you have a maximum of the magnetic field. And this is due to the fact that you could engineer the shape at the nanometer scale of this plasmonic nanostructure. So, in fact, on antenna, we discussed a lot of this, and what it is. There are many definitions of antennas. And one of the definitions says, okay, you have an emitter, which is a single emitter, or not, and you want to transmit in the far field the emission. So what I discussed just before is how you can locally modify the response of the nanostructure when you look just very close to what you consider the surface of the cavity, of the plasmonic cavity, or the antenna. The question that we will address here is how you can use an antenna in order to work far. I don't know if you have already seen SNOM. This is a very heavy apparatus, and you need to be a specialist of this to operate it. So that means that it's very comfortable to work with a normal microscope in far field. So this is what I will discuss here, is what you can do in far field by playing with antenna. So here you have the bow tie antenna. We have already discussed this. We know that here we have a very high electric field, and as we have a very high electric field, we will modify the emission. And for example, we can prove here, this has been demonstrated, that if you have an emitter which is in the middle, you can accelerate, because of this very high confinement, the emission by a factor which corresponds to 20. This is called the Purcell factor. You have at the same time the version of the Yagi-Uda antenna, the television's antenna, this nanoscale antenna. Here you have the nanometric version of this antenna. You put here emitters, quantum dots, and what you prove, just as you have at home, that the emission, direction of emission is changed. It becomes very directional. So that means by designing your antenna, you can do many things, activate specific field functions like acceleration, interaction with the matter, direction, and so on. In fact, what you have to consider when you discuss the interaction between matter or cavity, an antenna, and light, what you have to consider is the golden Fermi rule, which says that decay rate, the decay of the spontaneous animation, is a function of the field, the resonant field, and the dipole. And in that case, if you have a large interaction between the dipole, so the matter, your emitter, and the field, then you will have a large gamma. And this is the value of the gamma is a way to measure, to evaluate the fact that you have an high interaction. That's why we are very interested in the Purcell factor, which scales as the gamma, the decay rate, so the inverse of the lifetime, and in the antenna, and the decay rate that you can have in homogeneous media. And you can prove that this Purcell factor is a function of Q over V. Q, which is the quality factor of your resonant cavity, and V, which is the volume, modal volume of your cavity. And then you have two strategies. The first strategy is to say, okay, I want to work with dielectrics. And as I tell you, it's a very good strategy because the losses are low, and you can achieve very high Q cavities, typically millions if you are very good. The problem is that the volume is large. This is interferences, so that means it scales as lambda to the cube. So it's very large, in fact. But you can do this, and this has been done by putting an emitter right in the good positions. You have other strategies for which you can use plasmonics. You have losses, so the Q is not so good, but the volume are very small. We are discussing of volumes which are 10 nanometers to or less to the third. So this has been done in very lot of realizations, and I present here, for example, these realizations with a cube, silver cube, on a gold surface, and here they put a very thin layer of emitters and showed that the spontaneous acceleration is accelerated by a large factor. So, in fact, when you look more precisely at this Purcell factor, you see that you have Q over V, that we have already discussed, but you have other factors. And your first factor is this thing, spectral tuning. So if you are in the dielectric, it's not so easy because you know that the response is quite sharp. So plasmonics is much easier for this because the response is very large. You have the spatial tuning. If you have to put your emitter where you have the field. If you don't put the emitter where you have the field, you have no effects. So you have the question of positioning inside your antenna the emitter right at the good position is not a trivial question. Because in a plasmonic antenna, for example, the size of the antenna is 10 nanometers. So you have to be very precise for this. There are several strategies. What we use in my group is this, is in situ lithography. That means that you first look where is the emitter, then you do the nanoswitcher, which has been developed in the C2N by Pascal Sandlar. And the other question is the orientation of the emitter. If the dipole is like this and the field is like this, nothing happens, so you have to be careful with this. So we have a strategy for this. I will not go into the detail in this, but this can be controlled. So what I will discuss, if I have time, 5 minutes? Less? 10, good. Is this kind of antenna, so this is very close to the one that I present you with a silver cube. So here you have a gold substrate, here you have a patch, which is very thin, typically the size, the thickness of the patch is 40 nanometers. Here you have 1 micrometers, and the thickness, here you have a dielectric, 40 nanometers, so you see the antenna is big like this laterally, but it's very small in thickness. And here you put a single emitters, right at the good position by this in situ lithography system that I will not describe here. The fact that here, this is a modelization which has been done by Jean-Jacques Greffet in EOGS. Here, what I present here is a simulation of the field. Here you have the substrate, this is this. Here you have the patch, which is this, limited in size. And here you have the resonance. And what you can see is that you put an emitter just in the center here. You have a very high resonance inside the antenna, just because surfaces here are very close to each other. Typically 40, 30 nanometers or less. So we have a very high confinement, and what you expect is a very high Purcell factor. What we do here is we take, what we develop, we take here nanocrystals, colloidal nanocrystals, CDSE, CDS nanocrystals, which are made of a core of CDSE, typically a few nanometers of core, and it's surrounded by a shell of CDS. And they are synthesized in the LPUM, first by Benoît Dubertré and then now by Thomas Ponce. And these nanocrystals are in solution, so you can dilute the solution and deposit first on the gold surface one emitters, well, many emitters, but well separated, and then you put the patch white just above it. So I will say a few words about these emitters. The size of these emitters change the confinement, the electronic confinement, and the wavelength of emission. This is small size, this is big size. You can buy them as well, or obtain them by your collaboration. In our case, we work mostly with ones which are quite big and they emit in a weight 600 nanometers. They work at room temperature and they are very bright. The spectra is here quite large, well, large or not large, large compared to other quantum dots, to quantum dots that you can do epitaxial, but not so large for if you consider colloids, so 20, 30 nanometers of thickness. And when you look at this emitter, you can say, okay, they are quasi two-level system. In fact, you can say that we excite them in the blue, 405, 450, 70. We excite them in a continuum of states. So when you want to know the state of this, you resolve the Schrödinger equations and you find many because it's a quantum dots discrete level. But at what point they are so close to each other that you have a continuum of state. So you excite them in this continuum of state. You have a very quick, quasi-instantaneous, non-radiative transition to this lower level. And then you have the two level and you make a transition. So in some sense, we can say that we have a two-level system with this exciton X. So in fact, in order to simplify the thing, we can say that we have a pumping emission. And we can define two systems, the high pumping and the low pumping. If you are in the low pumping, you have low power, and you excite very slowly to this upper level. And once you are here, you can emit. When you are in the high pumping, you have a lot of power, so you get very quickly here. And then you have to wait for the emission. So this is the difference between low and high pumping. In fact, the low and high pumping can be defined as this. So here you have the number of photons of the laser per surface. And here you have what we call the absorption section. Surface section. So here, we can plot here as a function of gamma p, the emission of this. So when, as I said, when you are in low pumping, you pump very slowly and then you emit. So you are limited by the pumping, and you start like this. And when you are in the high pumping, once you have excited your exciton, you have to wait for emission. So you have a kind of saturation here. So this can be expressed, the number of photons that you detect, gamma d, can be expressed by this function. And here you can see it's linear and then it's saturating. And from this slope here, you can extract here the absorption cross-section. In fact, in the experiment, we don't work with gamma p, we work with p, but you can see that we can find the correspondence. So we did the experiment on one single emitters, and what we obtained is something which is quite normal at the beginning. So at the beginning we start with linear increase, then we have a saturation, okay. And from this linear increase here, you can extract the absorption cross-section, which is equal to this, and which corresponds to what we expect in the literature. So here we are, the scale here is micrometers, so we have between 0 and 1 micrometers, and we have this for a single nanocrystals. And here we have a strange thing. that I will not discuss here, which is linked to the fact that for high power, you cannot express your system at a single two-level system. But I will not discuss this in this talk. So we put these single emitters inside the patch antenna. And here you have the decay of single emitters when it's just on a gold surface. And then we take the same single emitter, we put a patch over it, and we measure again the decay. So the decay, when you measure, you excite with a pulse laser, and you detect the photons, and you count the time you have between the excitation and the emission. And from this, you repeat this millions of times, who are about a few tenths seconds, and you can construct this decay curve, which is the intensity of fluorescence as a function of the time. So this is what is called the decay curve. So this is quite long. Typical time, which is called the lifetime, which is 10 nanoseconds. And when you are inside the antenna, it's very quick. It's so quick, in fact, that we cannot measure it anymore, because here what we measure is the response of the system. So that means that we know that the acceleration of the spontaneous emission is over 200, because we are limited by the response of the system. So this proves that when you have an emitter like this inside an antenna, its interaction is very high. When you look at the intensity, we saw as well that what we get is much more photons that we expected. So we compare what we have before and after putting the patch, and we can see that the exaltation factor is a factor in intensity, a factor 50, which is very important. And this is due to fact that we excite many photons. It's not anymore two-level systems, the excitation which is increased, and the directivity. So we repeated the same experiment as before. We increase the power, and we detect the photon, number of photons, the intensity emitted by the antenna. And you see, you have the same curve. In fact, it's not exactly the same curve, because here you don't have microwatts, you have nanowatts. And you have the slope. And here, as you have changed from micro to nanowatts, what you can see is that the slope gives you the absorption cross-section, and you can see that you have win a factor 1,000 in terms of absorption, which is significant. So, and you can see as well this nonlinear part that I will not discuss here. So, okay, I think it's over. So I try to explain you what you can do with nanostructure, optical nanostructures that can be used for guiding, sensing, confinement, storage of energy, emission of light, and so on. So I give you some specific applications. Dielectric nanostructures are very interesting because they have low loss. That's why you can have a spectral sharp response. The limitation is the size of the volume, which is quite large, well, it's lambda to the cube. Platonic nanostructure is much smaller, but this is lossy. It's broadband. I don't know what is the best. It depends what you want to do, sharp response or broadband. And you can have high confinement and local intense field. Thank you very much.